Hey, AP Chemisters, this is Mrs. Vanderwalle with another blank wall. And section 1.5 talks about energy. We will talk much more detail energy in later chapters. This is kind of an intro to different energies that perhaps you remember from your time in physical science, or if you took physics, in the past. So let's talk about energy. Energy is known as the capacity to do work. Work is the action of a force through distance. You might remember the formula F equals ma. However, there are different types of energy. A lot of physics dealt with the energy of motion, where you can talk about 1/2 mv squared, if you remember that. We do, in a sense, talk about kinetic energy, but usually on a molecular level. Potential energy is energy due to position. Think about the book that's on the table ready to fall off. It's going to have more energy than a book that's already on the floor. So that would be your potential energy. We will talk much detail in this year about heat energy. That's your thermal energy. There's a whole branch of chemistry called thermodynamics, which again is the study of really heat in motion, thermodynamics, your heat energy. As you know, that heat will always go from hot to cold. There's your movement. And the last one is chemical potential energy. So it's similar to potential, as again due to position. We talk as far as chemical potential energy is the energy stored in the bonds of a molecule. So that's where the energy for burning propane would be, is the energy stored in the bonds, breaking bonds and forming new bonds. So we talked a little about that when we talked about what a chemical reaction is, or a chemical property where you have to, break bonds and form new ones. Anyway, that will be much more detail later on. You might remember that total energy is kinetic and potential energy added together. Very important concept. Energy is neither created nor destroyed. It only changes. And then objects tend to go from high potential energy to low potential energy. We can also phrase that objects in chemistry will tend to go from high chemical potential energy to lower chemical potential energy. It's more favorable to be in that lower group. Okay, so that's about it for section 1.5. So section 1.6 is the units of measurement. And so back in the 1700s, when Napoleon was in France, he actually had a committee form to come up with a more uniform system for measurement. He had a lot of problems on his hand, and he didn't have very happy royalty either because of the disputes over boundaries and what's a fair unified unit of, let's say, mass to measure their gold with or something. So this committee came up with 7 basic units. All right, and so what happened then later is that this worked pretty well for a couple, 100 years, and then in the 1960s, a new committee was formed and kind of tweaked Napoleon's. So let's see what they did there. All right, so the first unit of length or the first unit that Napoleon's group came up with was length, and they want to try to have a reproducible unit in a sense, or quantity that other folks could reproduce there. And so what they did is that they took the distance from the North Pole to the equator, and that's a pretty long distance. I don't think probably anyone has ever walked that. And they divided it by 10 million. So if you took the distance between the North Pole and the equator and divided it up into 10 million equal parts, that would be 1 meter. Okay, so the distance is 10 million meters from the North Pole to the equator. And that is still the unit of length today used. The unit of mass, what they did is that they took this length and they divided this meter, or first of all, they made a cube out of it. So they had a length times width times height. And if they try to fill that with water, no one could hold it and carry it, and that's pretty heavy. So they divided this length into smaller units, into 1/100th of a meter. They made a cube out of that. So that would be 1/100th of a meter cubed. And they filled it with the most common substance on Earth, which was readily available by most people, and that would be water. So the mass of this cube of water, they defined as 1 gram. And remember how I told you in the 1960s a new committee was formed? And this is one of those things they tweaked. They said instead of making it grams, because actually 1 gram is about the same mass as an M&M, which is kind of small and maybe not too handy. They said, let's make it a little bit bigger. So they decided to make it a kilogram. And I know that I haven't in AP chemistry told you what a kilogram is. You probably remember that from your first year chemistry class, but the idea of a kilogram is coming up shortly. A kilogram, if you want to jot this down, is also the mass of 1 liter of water, or 1 decimeter cubed of water. And it's much more handy, let's put it that way. Time is was defined as a second, and it still is today. However, it is more defined by the radiation of a cesium atom, and I really don't know what that is, but they still use a second, same second we have today. The temperature, this is one of those other scales that the committee in the 60s had tweaked and changed a little bit, but Napoleon's group came up with Celsius. And they did that by saying, well, where does pure water freeze? We're going to call that 0. Where does pure water boil? We're going to call that 100. And then, each degree Celsius is, 1/100th of that difference between the freezing and melting point of water, or excuse me, freezing and boiling point of water. So anyway, the committee then in the 60s said, I think we need an absolute temperature scale, and they changed it to Kelvin. So that's abbreviated by K. Amount of substance you might recall from your days from your first year chemistry class, and the amount of substance is and has always been defined as a mole. I always thought this was pretty clever. They abbreviate mole by taking off the E, so it's a 3-letter abbreviation, so big deal. Electric current, they defined as an ampere. We will talk about that later on. We talk about electrochemistry, and it's abbreviated as AMP. And finally, last but not least, is luminous intensity. We honestly don't ever cover that here in AP Chemistry, but the physicists are pretty excited about this. It's a candela, abbreviated as a CD. Now, those are only 7 units, but every other unit is based on those. So do you remember me even talking to you about kinetic energy? So kinetic energy, I said, is 1/2 mv squared. So we can talk about m as a mass. So we can talk about being a kilogram today. And then velocity, well, what is velocity? Meters per second. So you square that. So a kilogram meter squared second squared would be the unit for energy. And that would be then defined perhaps as a joule, which we'll talk about later. So yes, every other unit is defined from these 7. Okay, but now I also refer to as those prefixes. Let's turn the page and see what those prefixes are. All right, so oops, I forgot we have this little blurb here. So a meter again is a little bit more than a yard, and it's defined as 10 millionth of the distance from the North Pole and equator. Oh, by the way, it's also through Paris. Remember Napoleon was a French guy? We also call it the Rose line if you remember your Da Vinci Code. A kilogram is roughly 2.2 pounds, and again, it's really just the mass of water, 1 liter as a kilogram. The second was 1 out of 86,400 of a mean solar day. Where'd that number come from? Well, 24 hours, 60 minutes, 60 seconds, multiply those 3 numbers, you get 86,400. Now it is that periods of radiation of that cesium atom that I referred to. And Kelvin, there's your temperature scale. Notice that I changed this. You had a typo. Hopefully it's been fixed. So I fixed it on my smart or my notes here. But that is the actual formula for Fahrenheit. Here again, we can talk about the temperature scales and the relation between Fahrenheit, Celsius, and Kelvin. Folks, I will never talk about Fahrenheit here, so don't worry about that. And problem 8 and problem 9, why don't you go ahead and pause this, do those right now, and we'll talk about that tomorrow. So go ahead, pause this, work on this, and I'll meet you at the next page here. Okay, these prefixes may seem kind of familiar to you. It should bring back memories from your first year chemistry class. Sometimes we use more than others. So we try to, emphasize those that have special meaning for us. Just be aware that these are out there. You probably remember kilo, hecta, deca. Those are your 1,000, 100, and tenths right here. And especially if you're in the computer world, you would probably know what a mega is. Like the lottery is the mega millions. Today's computers, most of them are talking about gigabytes. Even there are some computers that will talk about terabytes. Here those are. And I bet some point, maybe when you're in college or just out of college, you'll probably have some petabytes in the computer world. So know that's your next prefix coming up. I hate to show my age, but the first computer I worked with and then in the 80s were like crazy. They were in kilobytes. And, you know, right now you couldn't even run your cell phone on a kilobyte. So think how much it's changed since then. So let's talk about what do those mean? Well, first of all, a petabyte or a peta anything, the symbol for peta is your capital P. And well, how big is this number? Well, there are 15 zeros following. So let's kind of see here. This zero right here is a million, billion, trillion. This is 1 quadrillion. You probably are not really familiar with that, but the exponential notation is 10 to the 15th. A terabyte, you ought to know what a terabyte is. Tera would be, well, a capital T, and there are 12 zeros following the one. So once again, that's a million, billion, that's a trillion, 10 to the 12th. So I bet you can figure out what giga means. Giga is your capital G, and that would be 1 billion. A mega, I've already referred to, is a capital M, and that's your mega millions, 10 to the 6th. Kilo is 10 to the 3rd, or just 1,000. And then hecto is 10 to the 2nd, hecto, 100, they kind of go together. And deca is DA, 10 to the 1st, so or just 10. So those are your multipliers in a sense to convert from a base unit or any unit into one of these larger ones. Notice something else, that once you get beyond kilo, these are all capital letters. And folks, there are prefixes even beyond pet. I think like a yottabyte would be one of them. That's a capital Y. So once you get bigger than kilo, they're always capital. So what about the smaller units? Okay, well, right here, this would be any base unit. So this could be your meter, this could be seconds, this could be moles, this could be liters, any derived unit, could be joules. So any unit, any base unit will go here, okay? And so we can subdivide these units. So deci would be a small letter D, notice it's small, which would be 1/10. What's another way to write 1/10? Be 1/10 or 0.1. 10 to the negative first. Centi is a small case c, which is 1/100th or 1/100. I guess I didn't feel like typing that out. Milli is 1/1000th or 1/1000 or 0.001. Micro, now micro is kind of a strange one here. Notice the difference. Look at its symbol. This is the only one that's the Greek letter. This is a small case mu, 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 and that is the symbol for micro. It is 1/1,000,000th. A nano is back to the English again, 1/1,000,000,000th. And a pico is 1/1,000,000,000,000th. Okay. So what I have asked you to do now is fill in the blanks here. So it says, remember, the smaller unit gets the bigger value. I'd write that down if I were you. So which is bigger, a meter or a centimeter? Well, the meter is. So that's going to be the smaller value. The centimeter is going to get bigger. Well, what was the multiplier? Oh, that was like 1/100th. So there's 100 centimeters in 1 meter. Which is bigger, a millimeter or a meter? Well, a millimeter is bigger, so this is going to get your smaller number. Well, what's the multiplier? The multiplier is for milli, oh, it's like 1/1000th. So 1/1000th of 23 is 0.023. A nano is a smaller unit than a meter, so this is a multiplier. So if I were you, I would just write, see if I can't do this here, 540. Notice I'm not doing it in proper scientific notation, times 10 to the negative 9th. And that's a times 10. And that would be all right, and your calculator can certainly handle that. And that's how I would treat those. So what I would do here is go ahead and work on these for me for tonight. And let me just pause again. Oh dear. Read through this. Here's your derived units. You can see where the volume came from, density, and just go ahead and try these problems. And again, we'll talk about these tomorrow. So for tomorrow, I'd like to have 1.3 through 1.6 done. Take care.